Swayam Prabha. Digital India. Educated India.
Hello, welcome back to another lecture on control systems. So in the previous lecture we have seen this diagonalizability condition, right. So we have seen that if the eigenvalues of a matrix A are all distinct, all the n eigenvalues are distinct, then you can always diagonalize it. On the other hand, even if they were not distinct, you could still be able to diagonalize it, but in some cases you may not be able to. But in cases where you may not be able to diagonalize them, at least you can get them to this nice looking Jordan block, which is basically a generalization of this diagonal version, right. So the diagonal form is a special kind of a Jordan block representation where each Jordan block is of size 1 by 1, right. That is what we have seen. We have seen that the tool that aids us in doing all of this is that tool we learned a couple of lectures back, this similarity transformation. One point, though I mentioned this earlier also, there is a bit of a digression, but about the similarity transformation that I think is very crucial to understand. See, you have a given transfer function, right. So let me draw that here, a figure would probably help. So you have a transfer function here, again the same way we drew earlier, you have a transfer function or an ODE given, right. Now from this, if you get two different state space representations, yeah, if you get two different state space representations, then it need not necessarily imply that there is some sort of a similarity transformation that relates these two, yeah. So that T may or may not exist, may or may not exist, yeah. On the other hand, if you have two state space representations that have a similarity transformation between them, so if this T exists which connects this SSR1 with SSR2, then we have seen that they must necessarily lead to the same transfer function, yeah. So this is not something that goes both ways, in the sense that you get two realizations from a transfer function, it does not mean that there has to be some similarity transformation that exists between the two. It will only exist if the realizations are minimal, something we have not covered or maybe not talked about and probably will not have time to talk about in this course. Minimality is essentially when a system's realization is both controllable and observable. Of course we have not even introduced what controllability and observability is. We have said quite a bit about it, but not really introduced it at all. We will do that in a later lecture maybe. But for now, this is important from the Jordan blocks perspective, because you might have some sort of a transfer function, right, where you see you can sort of realize it in one way and you might find that it is diagonalizable, yeah, but someone else might try to realize it in another way and finds that it is not diagonalizable. How is this possible? Now this can only happen if, so let me make it a little clearer. Suppose someone has written S minus A into S minus B upon S, or S plus A into S plus B for example, and this is S plus A into S plus C into S plus D. So suppose someone starts with this transfer function and someone else starts with the transfer function S plus B upon S plus C times S plus D. So this is say G2, yeah. Let us say this is S plus A squared and this is S plus A, right. Now you might say that, well, look, I mean this is just a pole zero cancellation after all, right. So what bad could happen in this, right. But you will see immediately that this fellow who is trying to realize this system with 4 states and this fellow who is trying to realize this system with 3 states, yeah, the first fellow may not be able to realize it in the diagonal form and might have to resort to the Jordan form of state space realization, right, whereas the second fellow will obviously be able to realize it in the diagonal form, right. So the same transfer function, one of them leads to a Jordan form, one of them leads to a diagonal form, and in fact the sizes of the state space realizations will also be different. So here is a clear cut example that shows you that you have the same transfer function in effect. Of course you might say that, okay, after cancellation is it still really the same transfer function, that is a bit debatable, but you see the way we view transfer functions from the input output perspective, no one would bat an eyelid if you were to cancel this s plus a, especially if a is on the left half, like minus a is on the left half plane, that is a is a positive real number, right. So from the input output perspective, the way we see classical systems, these two are the one and the same, they are the same system, the external description of both those systems are the same, but the moment you try to realize them in the state space domain, you see, I mean the question of a similarity transformation doesn't even arise here, because I mean for the simple reason that this dimension or the size of the A matrix will be different, yeah. So obviously there cannot exist a similarity transformation between the state space realization of G1 and the state space realization of G2, although they are essentially both the same transfer function or the ODE, yeah. So one will have a Jordan form, the other will have a diagonal form, of course of different sizes, right. So anyway, that is one point I wanted to really get out of the way in case I hadn't really clarified that earlier well enough. So then as promised, let us take an example today and start with an example of a matrix which does not lend itself to diagonalizability. So we have this matrix 1 1 2 0 1 3, I am deliberately choosing a triangular matrix because in that case the evaluation of the eigenvalues is pretty simple. So this one I urge you to check, yeah, that the eigenvalues of this matrix lambda will be equal to 1 1 2, yeah, because you just take s minus 1 s minus 1 s minus 1 here and this changes minus 1 minus 2 minus 3 and you take the determinant, yeah, and you do the expansion of the determinant and you will see it comes out to be s minus 1 squared times, rather lambda, I should write lambda, this characteristic polynomial will come out to be as lambda minus 1 squared times lambda minus 2, yeah, so you equate that to 0 and that will give you these 3 roots with one being a repeated root. So now fine, we have got this, so let us find out first the eigenvalue for the eigenvector for the eigenvalue say 2, okay. So what we then have is a, let me write down a here. So what we then have is 1 0 0 1 1 0 2 3 2 times V1 V2 V3 is going to be equal to 2 times V1 V2 V3. We have done this sort of calculation earlier, so it should be pretty familiar to us at this point. So what is this? This gives us, by equating the first element here, V1 plus V2 plus 2V3 is equal to 2V1. Second equation gives us V2 plus 3V3 is equal to V2 plus 3V3 is equal to 2V2, and finally the last one gives us 2V3 is equal to 2V3, yeah. So the last one really does not tell much of a story, it is identically true for every one of them, right. So let us choose, okay, we will choose that later. So let us get rid of the last one does not really say anything, right, it is identically going to be true. What about the first two? So from the first two you see I get that V2 minus V1 plus V2 plus 2V3 is equal to 0, and from here I get 3V3 is equal to V2. So let me substitute that 3V3 as V2 here, so I get minus V1 plus V2 sorry, I represent it in terms of V3, right. So I substitute 3V3 instead of V2 here. So I get plus 3V3 plus 2V3 is equal to 0. So I get V1 is equal to 5V3. Yeah. So let me choose V3 is equal to now 1. I have this freedom. The moment I choose V3 is equal to 1, you see V1 automatically gets fixed up as 5. Yeah, this leads to V1 5. And what about V2? V2 will also automatically get fixed up as 3. Yeah. So I will get this eigenvector and as I said, this eigenvector is really not unique. So I will get this eigenvector as 5, 3 and 1. Okay, that is the eigenvector corresponding to 2. What about the eigenvector corresponding to 1? Will I be able to find two linearly independent eigenvectors? If so, then I have hope of diagonalizing this. So in a moment we will see that our hopes will be dashed. So let us check. So we have once again 1, 1, 2, 0, 1, 3, 0, 0, 2 times let us say W1, W2, W3 is equal to just W1, W2, W3, 1 times that, yeah, because 1 is the eigenvalue now, earlier it was 2, so I had multiplied by 2, now it is 1. So therefore I get W1 plus W2 plus 2 W3 is equal to W1, yeah. So I can cancel out W1 from both sides, I can get rid of this, because I am lazy, I am not going to rewrite that, so I am going to get just 0 here. Second equation tells me W2 plus 3 W3 is equal to W2, yeah. So now I can get rid of W2, I can get rid of W2 from both sides and I get that W3 is equal to 0. What is the third equation? The third equation is basically going to tell me the same thing as this, is going to tell me 2W3 is equal to W3. So these two are not yielding anything new, it is just telling me that W3 is going to be equal to 0. And if W3 is equal to 0, what about this? W2 also turns out to be equal to 0. So then my eigenvector has to be just 1, 0, 0. Yeah. So I already took this example earlier, but you know, it is never a bad thing to sort of repeat yourself for reinforcement learning. Yeah. So then we get this as our vector W, which is the eigenvector for the eigenvalue 1, and that is the only eigenvector I get. There is no question of any second eigenvector. So how do I generate this second eigenvector? Here is where Jordan block will help me. So let me see, can I then write this, remember I wanted this W, so let me call this U now, I want to generate this chain. So AU is equal to lambda U plus W, where this W is known now and this U is what I am going to find, this is unknown, and I will see if I can solve for this. I should be able to solve for this if Jordan's theorem is correct, if the Jordan canonical form is indeed valid, this lambda is equal to 1 of course. So then now let me write this as 1, 1, 2, 0, 1, 3, 0, 0, 2 times U1, U2, U3 is equal to U1, U2, U3 plus W is basically my 1, 0, 0, yeah. So what is going to be my solution for this? So on the right hand side I have U1 plus 1, U2, U3. On the left hand side of this expression I have, what is this? U1 plus U2 plus 2U3, second one I have U2 plus 3U3, and third one I have just 2U3. As before, if I start from the bottom I get 2U3 is equal to U3, implying U3 must be equal to 0. When I plug that in the second equation I get U2 is equal to U2. So that is really not much, that is just identically true. So u2 could be probably anything. And now in the first equation I get, again I use u3 is equal to 0, so I get u1 plus 1 is equal to u1 plus u2, u1 plus u2, yeah. So now I can cancel out this u1 and I get u2 is equal to 1, right. So this third equation restricts my condition and now u2 has to be equal to 1, but what about u1, u1 is still free. See, now I got u3 is equal to 0, so this is 0, and u2 has to be 1, so this is what this second entry is, and the third entry I can choose u1 to be anything, I can choose it to be 0, I can choose it to be 1, I can choose it to be anything I please, right. So let me choose it to be 1, let me choose it to be 1. So if I choose this to be 1, now I am claiming that this is my entire transformation matrix is now cooked up. What is my transformation matrix? I first want to cook up the chain for the eigenvalue 1. So the original chain is, or the chain starts with the eigenvector, the original eigenvector, which is 1 0 0, then the second element in that chain 1 1 0, yeah, and then finally the last element in the chain is corresponding to the distinct eigenvalue, which is 2. So 5 3 1. So let me call this as my T matrix, right. So this is fine, then this is my T matrix, and of course the determinant of T you can check is 1. So if I want to find out the T inverse, yeah, so let me find the T inverse, compute the T inverse, transpose of the matrix of cofactors. So this is going to be transpose, first let me write the matrix of cofactors, I can't do it in one step, so I have to take 2 steps. The first entry is just 1, the second entry is I look at the cofactor, so 0, the third entry again is 0, the fourth entry here is I believe again 0, the last entry here is again 1, so plus minus plus minus plus, yeah, this entry here is 3 with a minus sign I believe, yeah, and this entry here is going to be 3 minus 5, so that is minus 2, and this entry here is going to be 1, I think we will have to change the sign, yeah, minus 1, and finally the central entry will be 1. So I take the transpose of this, so this is going to be 1 minus 1 minus 2, 0 1 minus 3, 0 0 1. I believe that should be T inverse. So let me now complete the calculation since I have been so elaborate in this calculation, yeah. So let us say T inverse AT, 1 minus 1 minus 2, so it is 1 minus 1 minus 2, 0 1 minus 3, 0 1 minus 3, 0 0 1, 0 0 1, and then I take the A matrix, which is 1 1 2 0 1 3 0 0 2, 2 0 1 3 0 0 2, and then I take the T matrix. T is 1 1 5 0 1 3, 1 1 5 0 1 3 0 0 1, yeah. So I look at this. Now this is my T inverse AT is equal to this, let us see if it is already taken me to the desired form, 1, the second entry is 0, hang on, I suppose I am not making a mistake, yeah, 5 minus 3 minus 2, yeah, first row looks correct, 0 1 0, yeah, it should be correct, 0 1, yeah, I think I am just checking if T inverse I have computed correctly by multiplying T and T inverse first by inspection. So 0, this is 3, this is minus 3, yeah, it seems correct. So let me just proceed with the usual computation now. So this is 1, so this is 2 minus 3 is minus 1, minus 4 that is minus 5 I believe, and then this is of course 0 and then 0 1, this is 1, and finally 3 minus 6, so this is minus 3 I suppose, and then this is going to be just 0 0 2 multiplied with 1 1 5 0 1 3 0 0 1. So this is going to be equal to 1 1 5 and minus 5, that is 0, and this is going to be of course a 0 times 1, 1 times 0, yeah, 0 as expected, 1 and 0, 3 minus 3 0, and finally 0 0 2. So this is exactly as promised, yeah, the Jordan form. You see, this is the 2 by 2 Jordan block sitting here corresponding to the repeated eigenvalues, right. This is exactly the form we expect, and we have got it here. So in this case there is only one chain, yeah, because it is too small a matrix after all, there is only one chain. You might have had multiple chains like we had shown in the previous lecture, in which case maybe you had a total number of repetitions of the root as 10 and you managed to generate 3 or 4 eigenvalues, right. So those 3 or 4 primitive eigenvalues, yeah, you can cook up their corresponding chains and they will generate individual smaller chains, yeah, so that they give you total that size of 10 dimensional subspace, 10 dimensional 10 by 10 Jordan block comprising of several smaller chains within of appropriate size, right, and that 10 by 10 block will entirely have an eigenvalue of 1 sitting within itself, yeah, that is the Jordan block. Now why is this so beneficial? Now you notice we want to answer the question as to whether this e to the jt is at all easier, in the sense that can we actually obtain the exponential of this in an easy fashion, yeah, is this easy to do? So that is our next goal, right. I mean, we have done all this Jordan block decomposition and all this, but is it really going to really be of much help to us, right? I mean, how can we be sure that this is actually any good? So for that you take this, you know, the way we have defined this is I plus jt plus j squared t squared by factorial 2 plus j cube t cube by factorial 3 plus so on and so forth. Now look at j squared, yeah, this is the curious bit. So look at j squared. So that is why I wanted to do this computation. Of course there is a very solid theory behind it which we are not able to cover in this course, because it will take us too far afield into linear algebra, which I do not want to do, yeah. So now look at this, right, look at j squared. What does j squared tell you? J squared will give you this 1 here on the diagonal, yeah, the second entry will be 2 here, yeah, and the third entry will be again 0, right, and what about the second case? It is going to be 0, yeah, 1 here and a 0 here, and the final one will be 0 0 4, yeah. So if you keep repeating this, yeah, I urge you to check this as a part of an exercise, yeah, that if you keep repeating this multiplication and you keep doing this Jordan multiplication again and again. So I will take the smaller block and I will show you. So this 1 1 0 1 times 1 1 0 1, what does this lead to? This leads to 1 2 0 2 0 and 1. Now if you again hit it with this another Jordan block 1 1 0 1, yeah, you will see this is again 1 and this is 1 2 plus 1, so this is 3, this is again going to be 0 and this is going to be 1. So you see the pattern emerges, right? You see the pattern immediately. What is this pattern? The pattern is that, well, the diagonals do not change, of course. So just like in the diagonal matrix, I mean the diagonal does not change here because it is unity. If this was d, then it would have been d squared, d cubed, so on and so forth. Yeah, that change would have happened. But the structure of the matrix does not change, the shape of the matrix does not change. The only thing that changes is this off diagonal entry gets augmented and it grows at a linear rate. Yeah. So this is actually not at all surprising, it turns out, right? If you had a bigger Jordan block, yeah, so eventually this turns out that this Jordan block, if you take the exponential of this Jordan block, what you will eventually get, for example, let me take the 3 by 3 block and I leave it to you as an exercise to convince yourself. So for example, if you had this lambda 1 0 lambda 1 0 0 0 lambda, yeah, suppose you had this, yeah. Now my claim is that if you take this as your j, then e to the jt will look something like this, yeah, it is exactly, the diagonals will be exactly like you treat the diagonal matrix, so in that sense it is very easy. What about the off diagonal? You see the first super diagonal will have terms like t e to the lambda t, t e to the lambda t, of course the sub diagonals will be 0, and the second super diagonal will have t squared by factorial 2 e to the lambda t. So it is basically like this is how it proceeds. If you take the Jordan block by induction or by otherwise also, you can check this, that if you keep proceeding with this Jordan block, yeah, eventually you will end up with a full triangular matrix, an upper triangular matrix in the exponential case, yeah, and when you end up with this upper triangular matrix, eventually you will see that as you go one super diagonal up, the degree of the polynomial increases, yeah, and grows by 1. So it is basically some t to the power k by factorial k e to the lambda t kind of terms that begin to appear as entries, yeah. The non-zero entries are of this form for some integer k, some positive integer k, yeah, that is all there is, right. So whether the system's eigenvalues are repeated or non-repeated, the only form of entries, so the e to the at, and this is very crucial. Now of course, now I am going to make suddenly another claim which will not be very much off. Now you have seen what e to the lambda t looks like, that is just going to be like e to the lambda 1 t, e to the lambda 2 t, so on and so forth till e to the lambda n t, and you have seen what e to the jt looks like, that looks something like e to the lambda t, e to the lambda t, so on till there is a block like this, and in the super diagonals you will have t to the lambda t like this, right, only terms like these, terms of this form, yeah. So these are the only kind of terms that appear. Now if you want to find any arbitrary e to the at least you know that it is transformable to a Jordan form even if it is not diagonalizable. So now if you want to find this, there is a corresponding Jordan form, and as I said, this diagonal form is a special case of the Jordan form after all. So whatever form you get it, whether it is an exact diagonal form or you get the Jordan form, it is nonetheless true that eventually this e to the at can be evaluated as this t times e to the jt times t inverse. But what is this t going to do after all? This t is, remember, a constant matrix, right, the entries of t are not functions of time, yeah, so they are not going to contribute anything insofar as time is concerned, right, they are only going to be constants. So it is going to be only sums of terms like these. So the entries, this is very crucial, later on when we discuss stability, this will be the key observation, yeah, and we will tell you why. Basically the stability of a state space realization totally depends, the asymptotic stability totally depends on the eigenvalues of the system matrix A, that is all there is, yeah. This will be a very crucial piece in that puzzle, we will see that later, maybe not in this lecture, but my crucial point that I am trying to make here is that now you notice that irrespective of whatever happens, whether it is diagonalizable or not, every entry of the exponential, matrix exponential has a form that looks like some polynomial times an exponential, and of course a polynomial in t times an exponential in t. That is it, that is all that the entries could look like, no other form could they take. Insofar as you are dealing with linear time invariant systems, that is everything there is to it, right. Now of course at this juncture you might feel like, okay, we have seen one method of getting the matrix exponential through Laplace inverse, we have got the second method through either diagonalization or through this Jordan form, right. So maybe this Jordan form you find it is a bit laborious, so is there a better way of doing this? So as it turns out there are several ways of doing this, but we will only discuss one more method of doing this, and that will make use of this famous result in matrix theory, is the Cayley-Hamilton theorem. So I will again not get into this, something called a Faddeev's algorithm, yeah, there are several other methods of doing this evaluating this matrix exponential, again for time constraints, and again because this is an undergraduate course we will not launch into all those methods, yeah, there are several numerically efficient methods, we will not get into that, we will only go for these methods that are grounded in solid theory where we can get some analytical results out of them. So we will talk about this third method for evaluating the matrix exponential in terms of the Cayley-Hamilton theorem. I want you to recall again that this matrix exponential holds the key to solving the state space equations, and therefore what we are doing here is indeed important, okay. Alright, so what does this Cayley-Hamilton theorem say? Okay, so the Cayley-Hamilton theorem just states that every matrix satisfies its own characteristic equation, that is it, simple. What does that basically say? You know, when you say every matrix satisfies its own characteristic equation, it basically means that in that characteristic equation, you know already what a characteristic equation is. So for example for A, chi A S is equal to determinant of Si minus A, yeah. So of course then if you want to say that the matrix satisfies its characteristic equation, then you have to basically say that in the polynomial you replace S with A and it turns out to be 0. This is what Cayley-Hamilton's theorem says. So the proof is actually a little long and we will not get into that proof, it is again available in standard books. Be aware however of the pitfall that sometimes people tend to take this very easy and say, it is very simple, just let me plug this is a fake proof by the way. Some people just say let me plug in this S here, instead of S let me put here A, and then I write A times I minus A and then take its determinant, and that is obviously equal to the determinant of 0, so it is 0, yeah, that is a fake proof. For one, for starters, you see the determinant, I mean this S is basically a scalar, that is alright, we actually replace the scalar with the matrix in the matrix polynomial. But you see what is this Si minus A, yeah, if you are multiplying this Ai, then basically you have this identity matrix which is this 1 1 1 1, and when you are multiplying it by S you are basically getting this S S S S like this. So if you want to replace this in this determinant here, then you better actually put in this A here, and then you cannot subtract anymore, no, because this is basically an n squared plus n squared matrix and you have this A here, yeah. So that is why it is a fake proof, I mean just simple check will tell you that the dimension, the size does not match, yeah, beyond anything else. So do not fall for this, the actual proof is there in all standard undergraduate textbooks of matrix theory or linear algebra, so please do go through it if you are interested. But suffices for you to remember that at this point the Cayley-Hamilton theorem says that find the characteristic polynomial of matrix equated to 0, yeah, that is how you get the characteristic equation. Now if you consider the matrix to be substituted in place of S in that polynomial, then you will get a matrix as 0, a 0 matrix at the right hand side. So remember this 0 here is basically an n cross n 0, okay, it is a 0 matrix, not just a 0 scalar here. When you are substituting this S, you are replacing this S with A here, what you get everywhere is a matrix, yeah, there is a matrix polynomial. So that is Cayley-Hamilton theorem, but why on earth should that interest us? Why, how is this Cayley-Hamilton theorem at all helpful to us? That is what we want to find out. So here is what we do. Suppose Fs and Gs are two polynomials such that Fs, maybe Fs is of a higher degree than Gs in general, greater than or equal to the degree of Gs, such that Fs can be written as some quotient times this chi a of S plus Gs. So notice that this is just a product where this is a quotient, yeah, this is a remainder, and this is the this is the divisor, not dividend, we call it the divisor again. The dividend is actually F, yeah, and this is the dividend. So essentially what it means is that you take this, you know, like we used to do in middle school algebra, right, you take this Fs here and you take this take this chi s here, yeah, so this is your divisor and you get this quotient here, yeah, so then you write this quotient times the chi a s here and you subtract it from this, what you are left with is then the remainder, yeah. So what is the property of the remainder? Recall that you would have continued dividing until the degree of the remainder becomes less than, strictly less than the degree of the divisor. It is just like dividing numbers, no? You take for example 5 and you divide 47, so then you get 5 9s are 45 and you stop the division at this stage because the remainder has a value which is less than the divisor, yeah. So no longer can you divide this remainder by the divisor and get an integer, that is why you stop. So similarly you stop here because now if you try to divide this Gs by this by this divisor, this remainder by this divisor, the Gs by this characteristic polynomial, then you will no longer get a polynomial as a quotient, you will actually get some rational function. So you stop your division, just like here you would have got a fraction if you had divided further, no longer an integer. Here also you would have not got any polynomial anymore. So therefore we observe that the degree of this Gs, yeah, this is strictly less than the degree of this chi a, yeah, because it's simple principle, just what you learnt in classes 7 and standard 7 or 8 when you learnt about this algebra, this division of polynomials, right. So the degree of the remainder, you keep dividing till the degree of the remainder gets lesser than the degree of the divisor, that is all there is to it, right. But this will be crucial to us. Now notice, let me put this in box here, yeah, there is an important thing here that is happening here. So this blue box, notice if lambda I is an eigenvalue of A, then here is the deal, you have f of lambda I is equal to this chi a of lambda I times the q of lambda I plus g of lambda I. But what do we know about chi a of lambda I? Of course the roots of the characteristic equation are nothing but the eigenvalues of A. So add the eigenvalues of A, the characteristic equation must equate to 0. So therefore this must be equal to 0. So therefore if lambda is an eigenvalue of A, then fi must be equal to g lambda I. Now what you might wonder, have we done out of this? What we have said is that if lambda is an eigenvalue, then f, which is potentially a higher degree polynomial, yeah, attains exactly the same value as a lower degree polynomial, a strictly lower degree polynomial, which is g. Yeah. So this is good, right, because now we know that the degree of g, yeah. So what do we know about this? Recall that the degree of the characteristic polynomial is n for a belonging to n cross n. So therefore the degree of this g must be strictly less than n. I will have a g polynomial which has at most a degree n minus 1, and one that also agrees with f, this higher degree polynomial, possibly an infinite degree polynomial, yeah. But it can always be captured at least at the spectrum. So we call this say the set of eigenvalues of, so the spectra of A, we call this lambda 1, lambda 2, so these are the lambda n, yeah. So this is called the, this set is called the spectra, yeah. So this is the spectrum of this matrix A. So at the at every value of the belonging to this set in the spectrum, that is at every eigenvalue, f and g must agree, f must equal g, yeah. So here is an interesting fact thereafter from complex analysis. So I am going to state this again without proof, again you go through your courses on complex analysis and you will find out that this is a standard result. So in general, if fs is analytic, so remember it is a function in complex variables, so this analyticity makes sense, is analytic in a region in the complex plane, in the Argand plane, it can be expressed as a, I should not call it a polynomial, as a series rather in the strictest sense. As a series, fs is equal to summation I is equal to 0 to infinity alpha I s to the power I, okay. So now of course I mean this is an infinite series, but it can still be divided by any polynomial, right, because it has the character of a polynomial. It is an infinite series, but each element wise, if I truncate it at a certain point, it is still a finite degree polynomial, right. So that's the deal here. So how does that help me here? Yeah. Now putting these two pieces in the puzzle together, observe now that, hang on, yeah. So observe, so this is it. Suppose you have f of A, now you are passing this matrix as the argument, yeah. F of A is given by chi of, so you pass this through this A into this characteristic polynomial, q of A is equal to plus g of A, alright. Now having done this, you might wonder how is this going to help us, how is this at all beneficial in any way, yeah. But now notice that because of Cayley-Hamilton theorem that we have just stated a while back, this again goes to 0, just like when you pass on scalar values, at the eigenvalues this agrees, yeah. So similarly here also when you put this A, this also agrees. So basically even if f is an infinite series, yeah, as soon as I pass the argument A, it can be always captured by a finite series. Why? Because GA, remember, the degree is less than n. So it will at most have entries like what? Alpha 0 plus alpha 1. So GA has, so GS looks something like this, alpha 1s plus, maybe I should not use alpha because I have used alpha earlier. So let me call it beta 0 plus beta 1s plus beta 2s squared plus dot 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 till beta n minus 1 s to the n minus 1. So no matter how high the degree of f is, even if it's an infinite series, I need no more than these n number of unknown terms, yeah, in order to express this series fa in terms of Ga. That's it. That's all there is to it. Now observe further that e to the s, yeah, e to the st, or rather e to the s basically, is an analytic function. So putting these pieces in the puzzle together, we know that if it's an analytic function in a region of this complex plane, it can be expressed as a series. Now we know that e to the s is an analytic function. Again, if you want to check this, verify. Go back to your classes on complex analysis and check what is the condition to verify analyticity of a function, and then verify that indeed the exponential function is analytic. So take this as an exercise. Not an exercise particularly pertinent to the control theory course, but still you should try to convince yourself maybe. So if this is an analytic function and any analytic function can be expanded in a series, then e to the s can also be expanded in a series. Yeah, there is nothing stopping me from doing that, right. So therefore, now putting this all of these things together in one go, what I then get is that f of a is going to be nothing but summation I is equal to 0 to n minus 1, yeah, beta I a to the power I, yeah. So when I say a to the power I, a to the power 0 is basically identity, yeah, that is the way I am taking the convention, yeah. Okay. So now how do we obtain these betas? That is the question. Once we have got these betas, I actually know what this, because remember my f of s is going to be e to the s, which is going to be given by this series, right. And now therefore when I want to find this e to the a, all that I need to do is know these betas, and that is it, I am done. So how do I get this? I know further that not only at a but at the spectra they agree. So let me take e to the lambda 1 t is equal to beta 0 plus e to the lambda 1 t beta 0 plus beta 1 lambda 1 plus beta 2 lambda 2 lambda 1 squared plus dot 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 till plus beta n minus 1 lambda 1 to the n minus 1, yeah. Likewise I can write lambda 2 t is equal to e to the lambda 2 t is equal to beta 0 plus beta 1 lambda 2 plus beta, sorry this is beta 1 no, beta 2 lambda 2 t lambda 2 squared plus dot 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 plus beta n minus 1 lambda 2 to the power n minus 1. Notice however that these betas, these have to be functions of time, okay. So this is one common place where students might often err. On the left hand side you have a function of time, on the right hand side apparently this is not a function of time, but it has to be a function of time. So these betas, they will depend on time. So then likewise you write all the equations like this, yeah, plus beta 1 lambda n plus beta 2 lambda n squared plus dot 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 till beta n minus 1 lambda n to the power n minus 1, yeah. So this is what we need to do. So one thing, first observation, how many equations are there? There are n equations. How many unknowns are there? Beta 0, beta 1 dot 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 till beta n minus 1, so that is n unknowns. So you have n equations and n unknowns, yeah. So you should be able to solve this, provided of course that the lambdas are all distinct. So this again I do not like, much as I would not like to use these results, but sometimes you often have to. So you will see that the structure of this thing e to the power lambda 1 t e to the power lambda 2 t dot 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 till e to the lambda n t, yeah. This gives rise to this form of a matrix. So we have sorry, beta 0, beta 1, yeah. So beta 0, beta 1 dot 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 till beta n minus 1, this is an n cross 1 matrix. So this is our unknown, yeah, and this is going to be like yeah. So this is going to be 1 1 1 1 1 1 like this. This is going to be lambda 1 square dot 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 till lambda 1 to the power n minus 1. It's going to be lambda 2 square dot 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 till lambda 2 to the power n minus 1 dot 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 like this till lambda n to the power n minus 1, lambda n. Now this matrix has a name, it is called the Vandermonde matrix, yeah. Probably we will also encounter this later, I do not know, if we do sufficiently, if we do get into controllability and observability with sufficient depth, we will probably also get into run into Vandermonde matrix again, but for now I leave it to you again as an exercise to check that this Vandermonde matrix is always non-singular if lambda I is not equal to lambda j for I not equal to j. So that means if you have all distinct eigenvalues, then this matrix is going to be non-singular, which means it is invertible, and therefore these betas, these coefficients can always be determined. But remember that these coefficients will obviously be functions of time, because then you will have this, let us call this matrix V, then your beta will be like V inverse this matrix e to the lambda 1 t, so on and so forth, e to the lambda n t. Now the trouble arises when you do not have sufficient number of distinct eigenvalues, just like we had to resort to Jordan form from the diagonal form. Here also it seems like it is trouble, right, but I will not really solve it in the general case, but show you one method with a particular example to illustrate that it is not really a big trouble. All that you need to do is a bit of differentiation, just a bit of an understanding of what is going on. You ultimately need n linearly independent equations, that is all, yeah. How you generate that, it is none of anybody's business, yeah. So how do you generate it when the eigenvalues are repeated? Then you will not have this beautiful Vandermonde kind of a structure to the matrix, yeah. So let us take this example, this I have worked out already. So this A is suppose 0 0 minus 2 0 1 0 1 0 3, okay, and we want to find e to the AT using this final method that we have learnt now, this Cayley-Hamilton theorem that we have learnt now, right. So how do we go about doing this, okay. So a quick check will tell you that determinant of lambda I minus A is equal to, I mean you can work that out now, because I have already worked it out, so I am not going to do that calculation here, I am just going to write it down explicitly here. It is going to be lambda minus 1 whole squared into lambda minus 2. So clearly the lambdas are 1 1 and 2, yeah, right. So now with this sort of a problem, now what do we do then, right, because now we see that if you had distinct eigenvalues, then this Vandermonde was guaranteed to be like invertible. But remember, this Vandermonde came about only after we wrote all these equations. So at this stage, can we do something to fix this situation? So let us take for example first the non-repeated case, yeah. So already we have say f at eigenvalue 1 is going to be e to the 1 times t, yeah, that is going to be this beta 0 plus beta 1 times 1 plus beta 2 times 1 squared. Remember the degree of this is the g, so the g is going to be, so the gs is going to be beta 0 plus beta 1 s plus beta 2 s squared. Why? It is only going to go up to the quadratic, the second degree, because this is a 3 by 3 system, so n is equal to 3, so n minus 1 is 2, yeah, and the degree of gs must be strictly less than 3, so it can have maximum degree of 2, so therefore there are 3 coefficients, this is beta into 1 squared, that is my equation 1. What about my equation 2? Let me take the distinct case first, then I get e to the 2t is equal to beta 0 plus beta 2 into 2 plus beta 2 into 2 squared. That is my second equation. Now I need a third equation also because I have 3 unknowns, beta 0, beta 1 and beta 2. So what do? What I do is essentially I take this first equation, which is basically due to lambda is equal to 1, and I differentiate this with respect to what? Well, of course with respect to the lambda. Yeah, so f lambda is equal to e to the lambda t. So what is f dashed of lambda? That is t e to the lambda t. Yeah. So I write f dashed evaluated at 1 is going to be t e to the power 1 times t. See, this t is appearing because of this differentiation now. But what is this? Right hand side also I must differentiate this. So f dashed must be equal to g dashed. Remember, this is very crucial. If a polynomial has repeated roots, we have also discussed this earlier also, right, when we talked about root loci, you remember, when we had like these the branches of root loci colliding, yeah, then we saw that that also gives rise to this breakaway points and break-in points, they give rise to repeated roots, and repeated roots means that as many repetitions as the number of derivatives that vanish. So if there is one repetition, that is if there is a multiplicity of 2 roots, then the function and its derivative vanish. If there are 3 roots, then the function, its derivative and its second derivative vanish. Yeah. So that way it ensures that if we follow this derivative approach, we will never run into trouble, because suppose instead of if this was a 10 cross 10 matrix which had 8 eigenvalues equal to 1, yeah, then at least up to the 7th derivative it would vanish. So I can take derivative 7 times and still be safe, right. I can still take 7 derivatives and I know that they must agree on both sides. So I can take 7 derivatives of f on the left hand side and 7 derivatives of g on the right hand side, yeah, because they must agree on those repeated roots. And that is primarily because this fellow, this characteristic polynomial, yeah, this has repeated factors. In other words, the characteristic polynomial has repeated roots. So therefore, how many derivatives of this will vanish along with the polynomial itself? As many times as the roots are repeated. If this has 7 repeated roots, or rather that means 8 roots in all of multiplicity 8, that means then the polynomial along with the first 7 derivatives of this will vanish. Yeah, so therefore we can apply the same technique, that 7th derivative of f and the 7th derivative of g, up to that 7th derivative, each and every derivative will agree at that value, right. Yeah, but what is the derivative of this on the right hand side? Gs. So g dashed s is nothing but beta 1 plus 2 beta 2s. Yeah. So let me just put this here. So then this is sorry, this I have carelessly overlooked this. This is beta 1. So then this is going to be 2 beta 1 times. So this 2 beta 1 is appearing because of this derivative term here. Yeah. And this again, this is due to 1, the eigenvalue 1, because we are evaluating at 1, plus, oh sorry, it's 2 beta 2, no, it's beta 1, my bad. So this beta 1 plus 2 beta 2 times 1. So this is my third equation, and now I have 3 unknowns and 3 equations. So let me try and solve them. So I have basically e to the t, e to the 2t and t to the t. Yeah, this is given by let us say the unknowns are beta 0, beta 1, beta 2. The first equation was 1 1 1, 1 1 1. The second equation was 1 2 4, 1 2 4, and the third equation was 0 1 2, 0 1 2. Yeah. So based on this, what can I write? Suppose this is just in the matrix form, but if I subtract 2 times the third equation from the second equation, then I get that beta 0 plus 2 beta 1 plus 4 beta 2 minus 2 beta 1 minus 4 beta 2 is equal to e to the 2t minus 2t e to the t. But that gives me basically this 2 beta 1 to minus 2 beta 1 cancels, this cancels, so I get beta 0 is equal to e to the 2t minus 2t e to the t, yeah, that is my beta 0. So likewise I have solved out the others, you please take that as an exercise to complete this solution, and I have found out that beta 1 is equal to, check my calculation, I might have erred also, it is going to be 3t e to the t minus 2 e to the 2t plus 2 e to the t, and beta 2 is equal to e to the 2t minus e to the t minus t e to the t, yeah. So having gotten this, we may then write e to the at as beta 0 times I plus beta 1 times a plus beta 2 times a squared, right, where beta 1 and beta 2 and beta 0 we have just evaluated. As I said, they would be expectedly functions of time, but before I write this expression down, of course you might try this on your own as an exercise, I will just write the final expression and hope that I have not made any calculation goof ups, okay, that is just my hope. But the bigger point that I want you to notice here is, notice the unity or the unification of the two methods that we have seen. We have seen that for such a matrix as this, where you do not have sufficient number of eigenvectors to diagonalize, you have to go for the Jordan form, and in doing so, in getting to the Jordan form, you end up with an e to the at matrix that contains terms apart from the exponentials. The exponentials are sometimes weighted or multiplied by polynomials. Here also, using this Cayley-Hamilton theorem, this method, you come to the same conclusion, because after all, what is this? Look, this beta 0 is this, yeah, so this beta 0 is this is going to get multiplied with, this is going to get multiplied with this identity, this is going to get multiplied with identity, then you have this beta 1 here, this beta 1 here, which is also going to get multiplied with this here, and finally you have this beta 2 here, yeah, this beta 2 here, which appears here with a squared. So all that this e to the at can contain are terms such as e to the lambda t, t times e to the lambda t, and t squared times e to the lambda t, if it is a 3 by 3 system, right, yeah, and that is also something that we can now establish from the Jordan form as well, we can verify, we now have a method, provided you believe me that every matrix has a Jordan canonical decomposition and similarity transformation of doing it, yeah, that always exists, that is a result, fundamental result in linear algebra, which obviously we are not going to prove, okay, that is left for a later advanced course if you take one in linear algebra or in higher or in multivariable controls or graduate level controls course, right. So the point is that I'll complete the story and I'll probably give you my calculation, you need not have to agree, in fact if I make a mistake then it's welcome that you actually point out that mistake. So yeah, this is what I found, 2 e to the t minus 2 e to the minus 2t, sorry not minus 2t, there can't be a minus 2t, right, yeah, my bad. So this is 2 e to the 2t, and then this will be e to the t, this will be 0, this will be 0, so this will be 2 e to the 2t minus e to the t and e to the 2t minus e to the t, yeah. So that is all the type of terms, so this is my e to the at matrix that I have found through my calculations, okay. So I hope that you have enjoyed these two new methods that we have learnt of obtaining this e to the at matrix. Please do a lot of practice, so just for practice you take up some sample matrices, you can always cook up some random matrices and try out these 3 different methods and see which one you are most comfortable with, which one takes the least amount of time for you, yeah. And I am not saying that one method is superior to the other, I mean it just might be me, right, I might be a little faster in calculating certain things and slower in calculating other things, right, you might find some other computation method easy. So whatever floats your boat, whatever you find more suited, do adopt that method, but it is always good to know multiple methods of arriving at the same result. In the next lecture we shall take a small digression from this studies of linear time invariant system and briefly venture into linear time varying systems, and thereby also show you in the process this unifying concept, and gradually we will specialize the case into linear time invariant and show that every result that we obtain for linear time varying system, yeah, actually translates to the known result that we have now for linear time invariant systems. Okay, the benefit of this state space method is that it allows you to handle linear time varying systems as well very easily. In fact, it allows you to handle nonlinear systems too. We will not have time to go into that, but at least this linear time varying system will do a bit of analysis of this and see that instead of this e to the at, we have something called a state transition matrix, yeah, that looks or behaves much like this e to the at, and in fact reduces to this e to the at when you consider the system to be linear time invariant. But in time varying case there are certain other challenges, yeah, but nonetheless it is interesting to know that there is a unifying theory of linear systems which this state space method allows you to get a handle over. So until then, take very good care. Thank you all.